Okay, so this is Psych 222. It is Monday, February 8th, and we are into Chapter 4. Now, Chapter 4 is titled Probability and Probability Distributions, and probability is vital to understanding statistics as well as understanding how science works. Because scientific evidence is influenced by statistical analysis, so we need to understand how probability works to quantify uncertainty. Now, in a sense, we all know what probability means because we use the word a lot in everyday use. For instance, let's start off with a really, really easy example. If I take a coin, okay, so I'm going to take a coin and I'm going to flip the coin. So there's two possibilities on the coin. There are heads and there are tails, okay? Let's assume that the coin cannot land on its edge. So you can either get a heads or a tails. Well, if we ask the question, what's the probability of getting a head on the coin? Okay, so let's imagine that before we flip the coin, we want to know what's the probability of getting a head. Well, most of us would say it's 1/2, okay, or 0.5. But the question is, how do we know that it's 0.5? Okay, so we need to think about this for a second. Why would you say it's equal to 0.5? Well, after you think about it for a while, you may come to the conclusion that there's actually no particular good reason to assume that the probability of heads should equal 0.5. So if we do not know that it's equal to 0.5, then how could we ever determine the probability of heads or tails on a coin? Now, one of the common answers given to this is that because the coin has two sides, okay, because the coin has two sides, that the probability is 1/2, that it makes sense that it should be 1/2. But that's not good enough because there's a lot of things that have two sides to them for which we wouldn't think the probability is equal to 0.5. For example, if I took, say, a ruler and I tossed the ruler up in the air, well, that ruler might not have a probability of coming up 0.5 on its right side because it's weighted a little bit differently. Okay, so if I take that ruler, and the ruler goes from say 1 to 10 inches or so, it might have a little bit more weight on this side of the ruler. Therefore, if I were to flip this ruler and throw it up into the air, there's no saying that the probability that it lands on this side should equal 0.5. Maybe that probability is actually a little bit higher than 0.5. We just don't know. Likewise with the coin, simply because it has two sides does not imply that it should equal 0.5. So the question is how to determine the probability of heads on the coin. How to determine the probability of heads on the coin. Well, one way of doing it, and one way we're going to see is actually used in statistics, at least in theory, is to flip many times. Okay, so we are going to flip the coin many, many times. So imagine on the first flip, okay, so here's the first flip. On the first flip, you get a head. On the second flip, there are my flips, you get a tail. Okay, so you have one head and one tail. Well, based on those two flips, you might conclude that the probability of getting a head is equal to 1/2 because it's come up half of the time heads and half of the time tails. But what's the problem with that? The problem with that is that we've only flipped it 2 times. Okay? We've only flipped it 2 times. So that's an insufficient number of flips. So then you say, well, let's flip it again. So we get our third flip. Okay, we get our third flip and that comes up ahead. And then we get our fourth, etc., etc., etc. And we keep flipping the coin. Okay, we keep flipping the coin over and over. Well, at some point, okay, at some point, as we keep flipping the coin over and over, we are going to get a pretty good approximation of the probability of heads on the coin, at least according to what we're going to call this relative frequency version of probability. And I will get to that in a moment. But for now, it makes sense intuitively that if I keep flipping the coin over and over and over, eventually I'm going to get an estimate of that probability. So the question is, how many times do I actually have to flip the coin? Well, we said that 2 times is simply not enough. And it makes sense that anything can happen on 2 flips of a coin. So then we said, let's flip it a 3rd time, a 4th time, a 5th time, etc. And the question is, how many times? Well, I'm going to suggest that we flip the coin in n towards an infinite number of times. As n, which is the number of flips, goes to infinity, and that's the symbol for infinity, so that's saying flip it forever, we will get the true probability of heads on the coin. And if that sounds reasonable, that's exactly the logic of probability that has been developed in statistics and in probability theory for the last about 300 years, is this idea that if you want to know the probability of something, you should continue to observe its events over and over in repetitions. Notice that what we've done here when we're taking n and letting n go to infinity is repetitions. We are getting repetitions of the experiment. Okay, whereas each flip is an experiment. So there's one experiment. There's one experiment. Here's another experiment, EXP, another experiment, and so on. And we obtain several repetitions of it to get the approximation of the true probability of heads or whatever we're dealing with, whether it's tails or any other event. And that approximation gets better and better as n heads towards infinity. So even if you got, let's say, 100, right? Even if you got, I'm just going to go down here, even if you got 100 flips, that's still not the best case scenario. The best case scenario is that this n should go to infinity. Well, you can think about that, and it doesn't take long to realize that you can never really get to infinity, right? So this becomes an entirely theoretical concept, that the probability of an event using this particular method is simply theoretical because we can never get an infinite number of experiments or trials for the given event, which poses some problems when you think about it, because how could we base a theory of probability based on an infinite number of events if we can never observe an infinite number of events? Yet nonetheless, in some cases, we're just going to assume that we can do that, because the idea is, why stop at 100? Why stop at 1,000 flips? Why stop at 10,000 flips? Why not just go to the total n goes to infinity? Okay. I think we would all agree that after 100 flips, the approximation of the probability is better than if we only had these first 2 flips. At 1,000 flips, the approximation is better than if we only had the 100 flips. At 10,000 flips, the approximation is better than at the 1,000 flips. So this is the logic of why it's tempting to want to go to that infinity idea, right? And that infinity, you can think of it as simply an idea. Okay. Let's liken this to a practical example. Imagine, let me just go down here. Imagine you want to know how reliable, right? How reliable your friend is. Okay. So you ask your friend, let's get together for a cup of coffee. So there's the coffee. And you say, well, let's, meet at 7 p.m. for the cup of coffee. And your friend shows up at 7 p.m. So there's one trial of the experiment, right? You just had one experiment with your friend and they showed up at 7 p.m. Therefore, that's pretty good. They're reliable so far, but that's only based on one experiment, right? That's only based on one experiment. So if somebody asks you how reliable is your friend, you say, I don't know, I've just had one particular experiment where they showed up on time. So then, of course, you want to do it again. Let's meet for coffee next week. And that next week, you set it for 7 p.m. and they show up again at 7 p.m. So you have another experiment, another experience with your friend in that way. Therefore, two times in a row, they've showed up on time. So therefore, you start to think they're reliable. And so on and so on and so on. And maybe sometimes they're late, maybe sometimes they show up at 7:15 after you take several different experiments and you get an estimate of that reliability. You can think of probability as working that way. In how would you know whether your friend is reliable in the long run, right? In the long run, you would have to have coffee dates, an infinite number of them, to know the true reliability of your friend. To know the true probability that they will show up on time, you would have to go to infinity. Okay. So that's the concept of much of the probability on which classical statistics is based. Okay, and we will return to that in a moment. The book gives some other examples here of where probability can be conceived and how you can think of probability. Probability is used everywhere. So they're talking about DNA sequencing. Um, it's used in medical procedures to estimate the success of medical procedures. They've used it in the vaccine research to look at how effective the vaccine is and what's the probability that it's going to work. It's used everywhere. It's used in science. It's definitely the basis on which statistics is built. Now, before we get to this relative frequency idea, this is the one we've just developed because it is the most important for the purposes of our book. This is the one that we've just developed, where the n is going to infinity, okay? So I'm just going to put n is going to infinity, and then we're going to unpack that pretty soon. This is definitely the most common. However, before we get to that one, there's another version of probability that we just want to mention here. It's not very useful for conceiving of modern statistics, but we still need to talk about it. The classical interpretation of probability is very, very easy. So let's take an example right here where I have numbers 1 through 6 on a die. Okay, so I'm going to flip the die, or not flip the die, I'm going to roll the die. I guess you flip coins. So I'm going to roll the die, and I want to see what number shows up. Well, there's my die right here, and I want to know the probability of that 6 showing up. So what's the probability of this one? Well, according to the classical interpretation of probability, I don't even have to roll the die. Okay, I don't even have to roll the die. I could actually just look at the die and say, well, everything seems to be the same on either side, make a judgment about the evenness of the die. So assume that the die is not loaded on one side and weaker on another side. And I could just look at it and say, well, 6 occurs one time out of a total of 6 possibilities. Therefore, the probability is 1 over 6. And that's why I said this version of probability is actually really, really easy because it's kind of like a precursor to this idea. Right? Remember that relative frequency we said as n goes to infinity? Here you don't do any of that when you think of the classical interpretation of probability. When you think of the classical interpretation of probability, you're simply just counting the number of possibilities of how it could happen. And you're saying, well, there's one way that 6 can come up, so it's 1 over 6. Likewise, if I want to know the probability of 2, well, that's 1 over 6 as well, because there's only one possibility of the 2. Now we can think of why classical interpretations of probability do not work, because they don't tell you anything about the long run, right? They don't tell you about this idea of n going to infinity. They simply just say, just look at the number of things you have on the die or in the bag, if you're maybe selecting balls from a bag, and assume they're all equally likely and just put that 1 over here. So there's your classical interpretation of probability. When we're talking about probability, we call each possible result an outcome or an event. Okay. Now, the events or outcomes can be defined a little bit differently as you get further into probability. But if we're to look at this die situation here, we would say that an event is a possibility before you actually roll the die. So there's an event, there's an event, there's an event. All of these are different events. So if we think of this whole thing here as being the sample space, right, this whole thing as being the sample space that we're working in, then we have 6 different events. When you actually obtain the event here, so actually after you roll the die and you get the 1 over 6, sometimes that's called the realized event. Okay, sometimes it's called the realized event, and we put the realized before the word event. Why is it called realized? Because it's actually happened, right? Before we roll the die, there are 6 possibilities, but then after we roll the die, we actually observe the single event, and that's called the realized event. Sometimes those names are not consistent across people who talk about probability, but you should be aware of it. Sometimes they're simply just called outcomes. Okay, they're just called outcomes. So we may talk like this is an outcome of the experiment, and before we actually rolled the die, well, we had 6 possible outcomes, 6 possible events. Okay, again, that terminology is not always standard from book to book and author to author. Okay, but you should be familiar with that. So we say that the probability of an event E under the classical interpretation of probability is computed by taking the ratio of the number of outcomes favorable to event E to the total number of possible outcomes. Well, there's the probability of event E. So there's, in our example here, that was the probability of that 6, to use our example. And that's equal to, well, how many ways can 6 happen? Well, we said 6 can happen in one way. So it's 1 over 6. This is exactly the idea of what we just computed up here. Now, as the book notes here, this depends on the assumption that all outcomes are equally likely, right? And in many cases, we just have to make that assumption. Is that 6 more or less likely than the others? Probably not, But then again, we don't really know, right? We have to make that assumption. Notice that's an assumption. So when we say what's the probability of getting that 6, notice how that's contrasting with this relative frequency idea that we just developed, right? How would the relative frequentists deal with this situation? They wouldn't just look at the die and say, well, there's one side that has 6, therefore it's 1 over 6. How would the relative frequency interpretation handle this? The relative frequency interpretation would say, well, roll the die, and then roll it again, and then roll it again. So you see that this relative frequency would take a first trial, a second trial, a third trial, a fourth trial, and so on until you get to n to an infinite number of trials. And then on each trial, they observe how often the 6 appears. Over that total n going to infinity, so theoretically assuming an infinite number of trials, we would see where that approximates. And it would probably, if we actually did it, right, infinite, flip it or rolling the die an infinite number of times would take a long time. So it's impossible, but maybe we can get 10,000, maybe even 100,000 flips. And eventually we'd probably find out it's equal to approximately 1/6. But we see these two ideas here of probability. And that's why the relative frequency interpretation is so common in statistics, because it makes a little bit more sense that if you want to know the probability of something, you have to observe it a number of times before you can get an estimate of it. You can't simply just look at something and make the assumption that all outcomes are equally likely, right? Because if you're going to assume that all outcomes are equally likely, well, then why are you actually trying to determine the probability of things if they're all equally likely? The idea of assuming that they're equally likely is a huge assumption to make. So that's why the relative frequency interpretation is so popular, because it allows you to gain experience with it. This idea that all outcomes are equally likely, that's kind of like assuming your friend will show up 50% of the time and not show up 50% of the time at 7 o'clock. You just don't know that. That's why you get the experience. So when you think of the relative frequency, you can think of you're getting experience, right? You're getting experience with the coin, with the die, with your friend meeting for coffee at 7 o'clock. You're actually getting experience. And what would be the ideal experience? The ideal experience would be to have an infinite number of experiences, so you can actually get the actual true probability. Okay, so that's an important distinction: relative frequency versus classical interpretation, to be able to contrast those two, how they're different from one another. So here we see the probabilities, relative frequency concept developed here, and the probability of event E is equal to approximately n of how many times it occurs over 6. Now, the book says approximately here because we think of the actual probability as the relative frequency over a very large number of observations or repetitions of the phenomenon. Well, I took that a little bit further than that. What's a large number of observations or repetitions of the phenomenon? What's the largest you can get? An infinite, right? So we took our interpretation to infinity, and that's where probability theory will lead you. It will not simply be a large number. You'll eventually go to this theoretical idea of infinity. But again, that stems from the idea that 100 trials are better than 10, 1,000 is better than 100, and so on. So just go to infinity for the most ideal. Okay. Well, there's another version of probability here, and that's called the personal subjective interpretation of probability. So the personal or subjective interpretation holds that probability is essentially a belief or opinion. Okay, it's a belief or opinion. Now, let's talk about what this means. I mean, it doesn't sound very scientific or rigorous to say that probability is a belief or an opinion. So, what was the probability that Tom Brady would win the Super Bowl yesterday? Well, at the beginning of the year, so let's go back to say September. What would you have said the probability is equal to? Well, maybe you figured Tom Brady's pretty good. So let's say the probability that Tom Brady wins is 0.60. So for now, if you multiply that by 100, you could say 60%. So this is Brady wins. Okay, pretty high probability considering how many teams are in the NFL and how competitive it is and how old Tom Brady is getting, but apparently he can still do it, right? So the probability is 0.60. Now, this probability that you gave in September was based on what? How did you derive this probability? Well, did you do it by the classical version up here? Did you do it by this version? Probably not, right? Probably not, because you probably didn't just look at how many times Tom Brady has been in a season and how many times he's won the Super Bowl. That wouldn't be a very good estimate, right? So let's say he's been in the league about 20 years, and he had won 6 Super Bowls up to now. You probably wouldn't just say, well, there's 6 out of 20, right? That wouldn't be a very good estimate. Why? Because that doesn't factor in things like his age, how competitive Tampa was this year, and other factors as well. Now, could you have done the relative frequency version, right? Could you have done this version? How would you have done the relative frequency version? Well, you can't really do it, right? Because can you flip the event? Can you replay yesterday's Super Bowl over and over, pretending like it's a new game each time, and see how many times Brady wins? You can't do that. So relative frequency is out as well. That's not going to work. So you can't do something like flip the coin heads, heads, tails, heads, 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 tails. You can't do that with this probability of Brady winning. So when they give you the probability estimate that Brady will win in September, and it's equal to 0.60, the question for us is, how did they get that estimate? Right? How did they get the estimate of 0.60? Now, they probably use some of that frequency information. They probably use some of it. But in the end, we'd have to concede that this estimate of 0.60 is not based on simply relative frequencies or the classical version of probability. It's based on somebody's belief or opinion. Maybe that belief or opinion has been informed by a whole bunch of things. Like maybe you personally know how motivated Brady was to win. Well, that helps form your probability estimate, right? So maybe your probability estimate was 0.58, and then you actually talked to Brady, and Brady said, I really want to win the Super Bowl. I am committing myself fully to winning the Super Bowl. Well, then maybe that increases your estimate to 0.60. But that information that you had from simply talking to Brady cannot be quantified in terms of a relative frequency. It has to simply be adjusted based on your belief or opinion about Tampa winning, okay, or Brady winning. I hope that makes sense in terms of how these belief probabilities can be used. Let me give you another example. They've been calling for an earthquake in California. Okay, the California big one, they've been talking about it, that there's going to be an earthquake in California, so big earthquake, all in California. So when you ask an expert in the area, that's the cracking of the earth. When you ask an expert in the area what the probability is of an earthquake in California in the next 20 years, the probability that they give cannot simply be based on prior earthquakes alone. It has to be based on forecasting future events of the earth, future seismology events under the earth, and that probability estimate is also going to be in part a belief or an opinion. Okay. Now, that doesn't mean it's not, I want to stress that doesn't mean it's not scientific. It definitely is. And the seismologists who are looking at this are basing it on very, very good evidence. But in the end, that probability estimate is going to have to incorporate a little bit of that expert opinion that is very, very difficult to put in terms of a relative frequency. Likewise, if you asked a clinical psychologist, if you ask the clinical psychologist what's the probability that their client will develop major depression or commit suicide or something like that, that probability estimate is not going to be based on flipping the event over and over and over, because you can't do that. So that's going to be an expert opinion, and that's going to be the belief or the opinion of the expert you're talking to. Economic predictions are like that as well. When you hear economists on TV talk about the economy, they don't quite know what's going to happen, and they can't flip the event. They can't get experience with the event. So it's going to have to be a little bit of expert opinion. Now, here's how you can think of things joining together here. There's heads and tails again for the coin. What is the probability of heads on the coin? Watch how we can put all the versions of probability and kind of talk about them together. What's that probability? Well, if we go to the classical version, it's 1/2, right? Because there's two possibilities, there's heads and tails, and you're just taking the one side over the two. So there's the classical version. What was the relative frequency version? Well, if you flip this 100 times, 1,000 times, 10,000 times, you'd probably find it comes out to about 1/2. Last, what is the subjective belief? What is the belief? Okay, give you a second to think about that. What's that personal subjective interpretation? Okay, those belief probabilities. Well, what would be your belief about the coin? You'd probably say it's about 1/2. Why? Well, because of maybe what you've seen with coins in the past. Maybe you take some of this information and you incorporate it into your belief. You say, well, it has two sides. They look rather even. Maybe you actually end up flipping it a few times. Maybe you flip it 10 times and you get 5 heads out of the 10 flips. In that way, you're using relative frequency information as well. But all of this information, you could say, is being used to support your belief that the probability of heads on the coin is equal to 1/2. So you see how you can use other information to get to the final conclusion of your ultimate belief in the coin. Now try going the other way. Can you go the other way? You can't go the other way, right? You can't. The belief probabilities, as argued by many, are the best probabilities because they can incorporate anything you like, including classical relative frequency information. So you might want to look at it like this, that this, you have subjective belief. Okay, these are subjective beliefs, and how you get to the probability of the event can incorporate relative frequency and any other information you want to, like classical versions of probability, maybe your opinion of you've heard something else about the event that can inform that subjective belief. Those things are very, very difficult to quantify. Going back to the Tom Brady example, it's very, very difficult to quantify Tom Brady's motivation to win simply by talking to him, but maybe you got a really strong sense by talking to Tom Brady back in September that he was really motivated to show that he can win while not being on the Pats and being on a new team. So that informs a subjective belief. So that's why many statisticians and philosophers will say that it's the subjective belief of probability that is superior because it can incorporate all those other probabilities and also things that happen that you cannot simply reduce down to a relative frequency. Now, what we've just said, some people would disagree with as well, because some people don't like to think of probabilities as being subjective. There are many people who think that if you cannot put it into a relative frequency, then you simply cannot compute the probability. They would not hold that subjective beliefs have any place in the determinant of probabilities. So there's debate on this, but this is definitely one way of thinking about it, that all of that interior information is contained within that subjective belief. Okay, so how do we find the probability of an event? Well, in this particular case, we're using the classical interpretation and the relative frequency concept to illustrate basic probability computations. So why did we spend so much time on looking at these different versions of probability up here? Well, we spent some time so you have an appreciation of what version of probability we're using when we look at examples. And many of the examples we look at and will continue to look at on Wednesday, they're based on pretty simple versions of probability, like the classical interpretation in some cases. But that doesn't mean that when we talk about probability this way, that this is the only way of defining probability. And it's important to be aware of that in simple situations, it's convenient to use this, but that there's also relative frequency and belief probabilities. So let's just look at a simple example here. Let's consider an experiment that consists of tossing 2 coins. So we have a penny and then a dime, okay, and observing the upturned faces. Well, what are some possible outcomes that we could get from this? Well, you can get tails for both coins. So that's one possibility of how things turn out after 2 flips. You can get a tail for the penny, a head for the dime, a head for the penny, a tail for the dime, and heads for both coins, right? Those are the possible outcomes of the experiment. So that's why the book says possible outcomes of the experiment. And now we're actually going to see the actual outcome when we conduct the experiment. So remember before when we talked about events and outcomes, events can be thought of as those possibilities. And then once you actually run the experiment and you get the outcome, right? Once you run the experiment and get the outcome, you can simply call that the realized event. That's the realized event. But again, that's not consistent across across how people talk about probability, but you should be aware of that before you actually run the experiment, here are the possibilities. That's why it says possible there. So we ask the question, what is the probability of observing the event exactly 1 head from the 2 coins? Well, again, assuming we're not going to flip this thing over and over, right? That's what the relative frequentist would want us to do. Remember, the relative frequentist would say, well, if you want to know the probability of getting 1 head from the 2 coins, you have to flip these coins several times to find out, right? That's the relative frequency. In this case, we're just going to reduce this down to a simpler version of probability. So 1 head from the 2 coins. Well, we're going to first assume, as the book does, that all 4 outcomes are equally likely, right? Again, that's a pretty big assumption, but we're going to assume it. That's why the book says it seems fairly reasonable that this assumption should hold. So there are 4 possible outcomes, and 2 of these are favorable for the event of interest, right? Because there's only 2 ways you can get 1 head from the 2 coins. There's one way, there's another way. So the probability of exactly 1 head is equal to 2 over 4, because there's 2 ways, 1, 2 over 4 is equal to 1 over 2. We've just reduced the fraction down to 1 over 2. Again, that's simply using that classical version of probability for that example. Because the event has a relative frequency interpretation as well, we could also obtain this result empirically using a relative frequency concept. Now, in this particular case, we are not actually going to flip the coin for real. We're not going to flip the coin for real because that would take too long. And because of computers, which we will soon be getting into after test 1, we can actually do things called simulations. So in the program we are going to be using soon, we do not have to know how to do this now, but let's just run through the example. We're going to give some code here that generates 500 2-digit numbers. Even digits will be designated as H, so an even number is designated as the heads, and odd digits designated as T. So we're going to get those 500 numbers and transform them into pairs of T's and T, okay? So when we do this, we set this up to say that the first digit represents the outcome of tossing the first coin. That's how the book is defining this here. And the second digit represents the toss of the second coin. For example, this number 36, that's a T for the toss of the first coin, and H for the toss of the second coin, because the 3 is odd and the 6 is even. That's how we're getting that. So when they do this in R, they get a whole bunch of numbers, right? They get a whole bunch of numbers, and then you're going to see even number, odd number, even number, odd number, and so on. And then after they do that simulation of tossing the penny and a dime 500 times, they can count up those frequencies of getting an odd, even, even, odd. So if it happens this way, right? Remember we said if it's a tail or a head, well, you're getting one of them. So those are the two events we're interested in, right? Those are the two events we were interested in. This did not count. That we didn't want the TT, we didn't want the HH. We wanted one of these. This is a simulation of that relative frequency. So remember, the relative frequentist would say, if you want to know the probability, then get some experience with it. Flip it. Well, this is the flipping, right? These are the flips. Now, these aren't real flips, right? Because it's done by a computer. So if we were to actually do this for real, we'd actually have to flip it for real. But this is, pretty close as a simulation. And oftentimes these things are done by computers now to try to give us an idea of what we would have. So it's simulating experience. All this up here is simulating experience. Okay, simulating experience with the coin. And when we do that, what do we find? Total frequency for this is 117, and the total frequency for this is 125. Notice one thing, that these two are not equal. Why aren't they equal? Right? Why is TH not equal to HT? You would think they would be equal, right? Why would one have more than the other? Well, there's no good reason why HT has 125 and TH has 117. It's just how things turned out in this experience. If we were to do the simulation again, these numbers would likely not be the same. That's why when you flip a coin, even though the coin could be perfectly fair, even number of heads and tails, even probability of heads and tails, you can sometimes get 7 heads and 3 tails. This is the same idea. That's why we're observing differences. And then we can add up those probabilities, and that number will become very, very close to the theoretical probability that we computed of 0.5. Okay. So there's an example of the relative frequency version of probability, but using computers instead. Okay. So let's end there for today. We've looked at the introduction to probability, the different interpretations of probability, classical, relative frequency, personal, subjective beliefs. Next week, or not next week, on Wednesday, we will start in with talking about the basic event relations and how probability is defined mathematically. Okay, we will see you on Wednesday.